Hello and welcome to today's video on the Calc 1 playlist. So today we're going to be starting our topics in calculus, and specifically we're going to be doing a little bit of a preface to mathematical induction, which will be in the next video. So before we get into what mathematical induction actually is, what it looks like, we need to have this concept of a material conditional being understood. So what is a material conditional? Then we'll go through truth tables, and then that will be kind of explained with an example. I remember when I was taking calculus, this was definitely a topic that was a little bit hard to understand, but bear with me and I'll try to do a good job of explaining what's going on. So, material conditional. So a material conditional is actually something very seriously easy to understand. It's a concept that's pretty easy to grasp. Basically, it states that if something happens, then we have this sign, then something else happens. So we have something that causes another thing to happen. So we can rewrite if this something happens, if A, let's call this if A, then B. So if A, let's say A is some action. If I get an A on my test, then my dad will buy me ice cream. So A being the getting A on test, A plus on test, let's say that. Then B is equivalent to my dad giving me ice cream. Hooray. Great, so simple enough. It's basically saying that if something happens, it causes then another thing to happen, if A then B. And moreover, we can kind of write this as P then Q. So this is read as if P then Q, where P is the premise, and Q is the consequence. So we have a premise and a consequence. So if P, then Q. Very straightforward to understand, but the truth table then gets a little bit tricky. So let's write out an example quickly and then talk about the truth table and filling this in and what it actually is. So let's do the example. It's Friday. And I get pizza. I'll write it better. It's Friday. If it's Friday, let's write it like that. If it's Friday, then I get pizza. Okay, great. If it's Friday, then I get pizza. So what are the possible scenarios in this case? Let's write out a table of values. So we'll have P, Q, and P material to Q as such. So the first case is I. So let's call this the first case. It is Friday. So let's say the day is Friday. So it is Friday, and then I get pizza. So if Friday is true, it is Friday, and then I get pizza, then this material conditional P to Q is true. Let's say it is Friday, so P is true, and Q is false. So let's say I don't get pizza. It's Friday, and I don't get pizza. Well, then we have to say that this material condition is false. What about in the case where it's not Friday, right? Let's say it's not Friday, so it's false. Let's do this. This is number 2, and 3 is it's not Friday, and also 4 will be it's not Friday. Well, I was not told about what happens when it's Friday, right? So for example, it's Friday, then I get pizza. So in the case that it's Friday and I get pizza, then Q is true. And in the case where it's Friday and I don't get pizza, Q is false. What is the material conditional then? Well, it turns out that the way material conditional is defined is it wants to be the most inclusive cases. So if you recall, when we were dealing with domains and ranges, we needed to have the range that is the most, or the domain that is the most restrictive to each function. Well, it turns out in this case, we need the least restrictive material conditional. So if we're not told anything about Friday, we then say that P to Q is true for both cases, because we don't know what happens when it's not Friday, right? And this might seem like a contradiction, especially for the third one. It's not Friday, but we get pizza. It's actually not contradicting our initial statement, right? Because our initial statement is saying that it's Friday, then I get pizza. Well, in this case, it's not Friday and you can still get pizza. It doesn't stop us from getting pizza. So our material conditional does hold true. So the only time it is false is if P is false. That is the only time it is false and Q is true. Then the material conditional is false. False. So again, that might be a little bit of a hard concept to understand. But again, we're not given information about what's happening on Friday in the case that it's not Friday. So for when Friday is false for these two, for case 3 and 4, when P is false, meaning it's not Friday, since we do not have any information about what's going on Friday, we are trying to have the most, most unrestrictive kind of set. So because we're having the most unrestrictive set, we then set that P to Q is true, because it can be true and it can be false. We don't know. We can't define something as we don't know. So then we just say, okay, then it will be held true then. So that's the way things are defined. And if it's a little bit trippy, we can do it again. We can do an example, and I'll work through an example again. We'll go back to the original thing that I said. Example, if I get an A+, then my dad will buy me a car. So P is being A+, and Q is equal to, let's draw a better Q. Q is equal to a car. Not even ice cream this time. We're going to get a car. Great. So if we have our truth tables here, then we'll go like this as such. We'll just draw some lines for our truth tables. We'll go probably need one more. So this is P, this is Q, this is P plus Q, or sorry, P to Q. Well, in the first case, when we have P and Q true, then this case is true. Why is that? Because I got an A+, so my dad gave me a car. He held up his end of the bargain. So I got a car. So P to Q is true. The conditional is true. Well, for 2, in the case that I don't get an A+, that I do get an A+ as well, I get an A+, and my dad does not buy me a car, well, my dad lied, and the material conditional is false. Sorry. That wouldn't make sense if it was true. Finally, let's say I don't get an A+, and my dad still bought me a car. Well, he didn't really break the promise to buy me a car. It's just I didn't get an A+, and he got me a car. So had I gotten an A+, he still may have bought me a car. It's not dependent on that. So we say that it's true because he didn't break his end of the bargain. And finally, for number 4, again, let's say I didn't get an A+, and my dad didn't buy me a car. It's false. Q being false. Well, again, had I gotten an A+, maybe my dad would have bought me a car, making it true. Therefore, we say it's true. So in the cases where we don't know, we don't have a set definition for our criteria, where we're trying to be the most inclusive and unrestrictive with our domain, we are saying then that if we do not know what the outcome is, we assume true. So that's why our material conditional is true in this case. The only time, I want to reiterate, the only time we have where our material conditional is false is if the premise is true and the consequence is false. It's kind of like breaking a promise. If you didn't hold up your end of the agreement, then your I guess the material conditional is false. And this video might not seem mathematical, but it's really important to understand for the next concept of mathematical induction. So don't worry, just stay tuned to the next video, and you'll probably get more further context as to why we're defining these conditionals and these material conditionals as such. So that's all for today's video. Try to keep it brief. Feel free to leave a like, a share, subscribe if you learned something new or if you enjoyed, and I'll see you in the next video. Thank you.